Okay, anybody have any homework questions about thermo? Yeah.
Number 2 on where you just inlet control.
Yeah. Number 2. Okay. So you have a nozzle. It gives a pressure at the inlet and a temperature at the inlet. So, and it's steam. So if you have a temperature and a pressure, then if you're assuming ideal gas, you can use the ideal gas law. So that's one thing that pops into your head. And otherwise, we have tables for water too. And so you can use those values to look up. You'd have to convert them, which is sort of a pain, but that's not a big problem. And it gives us a speed coming in, and then it gives us a pressure and a speed going out. And we want to figure out the exit temperature. We're ignoring any height differences. Okay. Well, let's just start going through this equation. So this is control volumes. One, number 2. And it's a nozzle. Which means that intuitively what we're doing is kind of exchanging a difference in enthalpies for a difference in speeds. I'm going to start with the full equation. So dE dt for the control volume is equal to Q dot minus W dot for the control volume plus, okay, did it say steady state anywhere? Hopefully, yes, steady state operation. So I'm going to just write this right from the start as m dot. This is going to be equal to 0 too. So m dot times enthalpy at the inlet plus the speed at the inlet squared over 2 plus gz at the inlet minus m dot times the quantity h at the exit plus speed at the exit squared over 2 plus gz at the exit. It said that it was well insulated. So like you're always going to do every time you use this equation, you're going to look for the stuff that cancels out. This cancels. This goes away. And it says ignore potential energy effects. So those two cancel. And we're down to, 1, 2, 3, 4, 5, 6 variables. Okay, well, what do we know? We know the pressure and the temperature. So that is enough for us to look up. Oh, and we know the speed. Okay, so I'm going to start just writing what we know. This is given. Okay. This we can look up in a table. Okay. And what do we know at the exit?
Velocity exit.
Yep. And pressure. So this is given. Does it say anything about the state? We're trying to find the temperature. It doesn't say anything about the state. So as far as we know, it still could be superheated vapor. And then we don't have enough information. So, well-insulated nozzle. Okay, this is a nozzle. It's just a rigid thing. There's no expansion or anything. There's no electrical work coming in or anything like that. So this goes away. All right, so let's simplify this. Since everything's gone away except stuff divided by m dot, we can cancel the two m dots. I mean, basically what we're doing is dividing both sides by m dot. Okay. And what we're left with is HE plus VE squared over 2 is equal to HI plus VI squared over 2. This is given. This is given. This is in a table. And that lets us calculate this. And then once you know H, given that you know the pressure, you can do a reverse lookup on the temperature in the table. So now at the exit, you know the pressure and you know the specific enthalpy, and you can do a reverse lookup to see what the temperature is. In the table. Okay? Does that help? Okay. So I would have done it except with all the unit conversion and stuff. I didn't feel like it. Okay, but that's how you do it.
Make us struggle a little bit, do it ourselves.
What?
Make us struggle and do it ourselves.
Yeah, right. Any other questions about homework?
So that, number 4 is like a sort of like that this was compared to number 1.
Number 4. Okay, well, the fact that it says refrigerant 134A, and that's one of the small number of things that we have property tables for, almost 100% tells us that we're going to look that up in a table, look up something. So just keep that in mind. That just tells you, like, look for what properties we have. Do we have enough information here or here to look stuff up? So this is a diffuser. It's saturated, which means, what does saturated mean for something that you can look up in a table? I mean, it's just practically speaking for the table. It means that you only need one property to look stuff up. So then it says it has this velocity, but it doesn't give a pressure. Oh yeah, it does. There's the pressure right there. So we can look up anything we want, any property we want at the inlet. At the exit, it gives a pressure. It doesn't say what the state is. Determine the exit temperature. Okay, well, it is a diffuser, so the pressure is going to go up at the exit. But let's think through this one a little too. Okay, and it said it was steady state, right? So this is going to be 0 because it's steady state. That's equal to Q dot minus W dot plus M dot times HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. And it's insulated and it's a rigid thing. So this goes away, this goes away. We're ignoring potential energy, I think. Yeah, ignoring potential energy. And it says that the velocity is negligible after it comes out. So we're going to treat this as 0. We're going to cancel these two. Divide both sides.
Just freezes in here.
Yeah, right. Well, you know, we saw, like, when you do calculations of the kinetic energy, things have to be going pretty fast for the kinetic energy to be on the same order of magnitude as enthalpy or whatever. So divide both sides by m dot, and we get H E is equal to HI plus VI squared over 2. It's at the inlet, we can look it up in the table we said, and we have the speed. So this is something we can look up in the table. This is given. That lets us calculate the enthalpy at the exit. We have the pressure. So if you calculate enthalpy at the exit, we know the pressure at the exit. And again, you're going to do sort of this reverse lookup thing where you're looking for an enthalpy and seeing what temperature that matches up with. Okay. Any questions about that one?
If I gave you, because I get up to that point where I have the enthalpy and pressure, and then I see that it's like in between a bunch of numbers, so like I
Oh, yeah.
interpolate in too many things.
Right.
If I just give you them, could you just like roughly just set it up? You don't have to do like the whole thing.
Yeah, sure. Well, hopefully the pressure that they give is one of the pressures in the.
It's between two of them.
It's between two pressures.
The one I got 20.69 bar.
Okay.
So it's like half. So it's a little bit over 2 megapascals, but.
Right. I would just use 20 for that.
Okay, I think that's why.
That's right. And then you can interpolate just on the temperature.
That makes sense. Okay.
Yep. I think that's the intention of that. Is you're like, okay, it's there in the table, so now it becomes a one-dimensional problem.
Okay. Thank you.
Okay. So now I want to finish. We have done. Okay. So for the devices that we're doing, we've done nozzles and diffusers. We've done turbines. And so the last thing we have to do is compressors and pumps. Okay, well, these are very similar ideas. A compressor deals with vapors, gases, and pumps deal with liquid. And compressors, so there's two things that you can be dealing with here. First, compressors and pumps can both produce a higher exit pressure. And then pumps can do another thing that you don't see done with compressors. Pumps can also move liquids to a greater height. Okay, so let's go through the standard simplification of compressors and pumps. Standard. Okay, so first I'm going to go if what you're doing is increasing the pressure at the exit, producing a higher pressure than at the inlet, I mean at the exit, then at the inlet. So here are the assumptions that you're generally going to make. dE dt is equal to Q dot plus W dot plus Mi dot times the quantity Hi plus Vi squared over 2 plus GZI minus Me dot times the quantity He plus Ve squared over 2 plus GZE. Okay, so that's the starting point. And we're going to assume first, steady state. And so that makes this go to 0. The I and the E go away, and we just have the one M dot. We're going to assume that there's no significant heat transfer. We're generally not concerned with speed, so we're going to assume that the change in kinetic energy is 0. So that goes away. These two cancel. And since the first one we're doing here is just producing a higher pressure at the exit. We're not concerned about the height, okay? So the change in potential energy, we're gonna set to 0. So these go away. And what you're left with is exchanging work for enthalpy. So this simplified model says the rate of work is equal to, and actually let me write this in a different form. You can keep it over here. Negative work CV, okay? So I'm gonna move the W dot over to the left side of the equation, and that's equal to M dot times the quantity H at the inlet minus H at the exit. Notice that this is fundamentally the same equation as the turbine. But a pump is very different from a turbine. So what's going on in this that's different from a turbine?
Enthalpy instead of kinetic energy.
I think actually, yeah. So both of these two sides are positive. So it's the same. It's the same quantities in there, but a turbine does work on the surroundings. Whereas a pump inputs work from the surroundings. It can either be mechanical work, you can make mechanical pumps, or it can be electrical work. So a compressor or a pump inputs work from the surroundings. Okay. Let's see if I have a problem for that. Yeah. Okay, so let's say you have a compressor. At steady state. And we're going to ignore kinetic and potential energy effects. So we're going to ignore the change in kinetic energy and the change in potential energy. And at the inlet, we're given that the pressure is 1 atmosphere, or 1 1 atmosphere is the same as 1 bar, I believe. So 1 times 10 to the 5th pascals. And the specific enthalpy at the inlet is 290 times 10 to the 3rd joules per kilogram. And M dot is 0. Let's say this is given at the inlet, and this is equal to 0.1 kilograms per second. And then at the exit, we're given that the enthalpy is 1023 times 10 to the third joules per kilogram. And we want to know, so this is the standard simplification. But we want to know if we're given that the electrical power, because it's pretty easy to measure electrical power going into a device. If you measure that and the rate of work is 77 times 10 to the third watts going into the device, into the compressor. What's Q dot? Okay, well, we know we're not using this simplified form of the equation completely because it doesn't have a Q in it. It doesn't have a Q dot in it. So we're going to have to do the simplification ourselves and just, base it on what they said we're assuming. It's steady state, so I'll cancel that right now. We know we need to leave Q dot in there. The rate of work is given. Is W dot going to be positive or negative?
Positive, negative for the compressor.
Yeah, so for any compressor or pump,
Or pretty much
yeah, W dot is always going to be negative. So we're going to write this as negative, minus negative 77 times 10 to the third. Okay, you with me on that? And then it's steady state, so there's only one M dot. So we have plus 0.1 times the quantity. Enthalpy at the inlet is 290 times 10 to the third. Plus, you have this stuff, but we're neglecting these two contributions. So forget about that and that. And then we have minus 0.1 times the quantity. Enthalpy at the exit is 1023 times 10 to the third. These two terms go away. And you're left with an equation that you can solve. So if you go through that calculation, you get that the rate of heat transfer in the control volume is negative 3,700 joules per second. And joules per second is watts, of course, you can write it like that. Is that what you would expect, a negative value for Q dot? I mean, yeah, if you have a device and energy is being lost, there are inefficiencies, you're going to expect the device to heat up, and that heat is going to dissipate to the surroundings. Anybody have any questions about that? Okay, so this was all for the case, a pump or a compressor, where you're trying to raise the pressure. If it's a pump, you do it exactly the same equation and everything. So now we're going to deal with the case.
That W plus instead of negative in that equation?
In which one?
That equation, the regular equation, the whole CV equation, you put plus W, the rate of change?
If
A little bit more?
if you're raising the height of a liquid, you mean?
No, in the.
Oh, I gotcha. So instead of doing the negative and the negative,
Yeah, but where you wrote it out, you put plus W
At the top.
at the very top.
yeah, I didn't really know how to write that.
No,
Because I was trying to make
like in
this.
the full DE over DT CV, the full CV equation that you wrote.
Oh, I did? Oh, thank you. Yeah.
Okay.
Okay.
Just trying to prevent.
Yes, thank you.
down the line.
Yes, thank you. Okay, so now we're going to go to the second case.
Would that not make when you do the assumptions, would that make W positive instead of the negative W, or does that assumption still say the same? Right?
Let's see. No, I just kind of glossed over it. Let's see. Then oh, you're right. That it should be, well, yeah, thank you.
Okay.
It does, because, you know, you're definitely going to have a higher enthalpy when you have the higher pressure at the exit than you do at the inlet. So this should be HE minus HI. Yep. Okay, so now we're going on to the case where we have a pump, so we're only dealing with liquid. And we're using it to raise the height of a liquid. The assumptions that we're going to make first, steady state. And so dEdt is 0. And mi dot is equal to me dot is equal to m dot. We're going to tend usually to assume that there's no heat transfer, so Q dot for the control volume is 0. We're still going to usually assume that there's no change in speed that makes a big difference, the kinetic energy. But now the potential energy is going to matter because we're changing the height of the liquid. So the change in kinetic energy we're going to assume is 0. And then the last thing we're going to do is, we're going to consider our system not to be like the machinery of the pump anymore, but we're going to consider it to be kind of the two ends of the hose, if you think of something like pumping a liquid out of a pool or something. Okay, what? Yep, right. So if you think of it that way in your system, you're drawing a boundary around everything, including the inlet, the entire inlet hose or pipe, and the whole exit hose or pipe. What do we know about the pressures at those two? You know, I mean, say like, okay, so if the pump looks like this, and you have a hose that's getting water from down here, and then it's distributing the liquid up here. And that's like some small number of feet. And our system is not going to be just the electrical device, but it's going to be this whole thing. Well, then in both cases, the pressure at the inlet and the exit is just the atmospheric pressure. And so we're going to assume that enthalpy doesn't change. Okay, so if we start with the full equation, and then minus the exit stuff. This goes away. It's just an m dot. That's all because of steady state. We're assuming that there's no heat transfer. The work is electrical work coming in. We're assuming that the two kinetic energy terms cancel out, and we assume that the enthalpy cancels out. This is the first one. Every other equation, simplified equation that we've seen uses enthalpy. This is the only one that doesn't. And we get negative W dot for the control volume is equal to m dot times the quantity GZE minus GZI. And both of the sides of this equation are positive. Okay, so an example of this, let's say water, liquid water, is lifted 5 meters. At a flow rate of 0.5 kilograms per second. If the system is in steady state, what's the power required? Well, this is one where it doesn't tell us what stuff we can cancel. So we'll write out the full equation, we'll see what we have, and then in order to get, you can only solve for one variable with an equation. So then we'll start thinking about, based on our standard assumption, what are the things that we can cancel probably to get an answer? You know what I mean? So we'll start with the full equation, dE dt is equal to Q dot for the control volume minus W dot plus the mass flow rate is 0.5 and it's steady state. So that's the same for the inlet and the exit. We don't know anything about the pressure or the temperature or anything like that. Well, let me just start writing stuff out. So H at the inlet, plus VI squared over 2 plus GZI minus 0.5 times the quantity HE plus VE squared over 2 plus GZE. Steady state, so we know we can get rid of that. We know that, okay, so 0 is equal to Q dot minus W dot plus, I'm going to group these together, 0.5 times let me make that a bracket. Okay, so we have HI minus HE plus VI squared over 2 minus VE squared over 2 plus GZI minus GZE. Well, this is one, we know this one, right? So this is equal to, we have a higher value at the exit. So this is going to be minus 5 times 9.81. All right, are you with me on that? We're trying to calculate this work. So now we have to think about what kind of things are reasonable to cancel. Well, in the standard simplified model, we assume that there's no heat transfer, so we'll get rid of that. We assume that there's no change in enthalpy, so get rid of that. We assume kinetic energy doesn't make a big difference, so we'll get rid of that. And now we have an equation that we can solve. Okay, so negative work is equal to positive 49.05. Whoops, I left off the, so 0.5 times positive 49.05. And so W dot is equal to 24.525 watts negative. And that negative makes sense because that's electrical work coming into the pump. Any questions about that? Okay. Well, that is it for those 5 devices. And I'm going to stop there for today. And then next time we'll go through a detailed outline of all the topics that we've covered up until now and just try to refresh our memories on what equations we have, how you can work with these, how they fit together, that kind of stuff. Okay? Have a good weekend.